What's up, good people? This is section 6.4, Graphing Radical Functions. This is your boy, Mr. Bergman, coming to you from my basement. All right, so we got what we really want to do here is we want to graph these radicals for the first time ever. We're going to see some parent. These are new parent functions. You can see the square root of x, and I just want to remind you that anytime we are taking, anytime we're graphing things, or anytime we're using functions, that we're not going to be using imaginary numbers, because what are we going to do if we get an answer of negative 3i? Where are we going to put that here? We just can't. There's no space for imaginary numbers on the real plane. So we're just going to ignore the fact that we really could take the square root of negative 4 and get 2i. But we're not going to. We're only looking for real numbers here. So if you put negative 4 into this function, you can't get anything. It can't get any real number out. Negative 1 doesn't happen either. The action really picks up when you start at 0. So you can take the square root of 0, you get 0. You can take the square root of 1, you get 1. I'm going to choose not to go like 0, 1, 2 here, because it'll just make it be a lot easier if we choose perfect squares as inputs. The square root of 4 is 2, square root of 9 is 3. And you can plot them. This is the point 9, 3 right here, the bottom row. 4, 2 gets plotted right here. 1, 1, 0, 0. Great. Let's take a look at cube roots. Again, I'm going to only choose perfect cubes over here because I don't really want to plot any decimals. So if you choose perfect roots over here, then that means you can take all the cube roots and then you get the answers over here. So 20. What's the cube root of 27? Well, that's like what number times itself 3 times is 27? That's 3. What number times itself 3 times is 8? That's 2. The cube root of 1 is 1. The cube root of 0 is 0. The cube root of negative 1. What number times itself 3 times is negative 1? That's negative 1. What number times itself 3 times is negative 8? That's negative 2. You actually can take cube roots. Whenever this radical, whenever the type of radical is an odd number, you can actually work with negatives here, and that's fine. So you can see it actually extends. This is the point negative 8, negative 2, the top row. This is the point negative 1, negative 1, 0, 0, 1, 1, and 8, 2, right here. It gets plotted, and the curve looks like this. It's kind of an S shape. It is a function. It passes the vertical line test. All vertical lines only touch the point. Even here along the y-axis, there's only one point, even though it gets super steep. And it does pass the horizontal line test as well, as we'll see. Let's actually talk about the properties of each of these functions. I'm going to move myself up here. And so this is what, here's what the functions look like. So let's talk about the parent function square root of x and the cube root of x. The transformed versions of that would be, you can put h on the inside, k on the outside, and the transformed version would be a, like the vertical dilation a would be over here. What is the domain of this function? The domain of the square root function would start at 0. The lowest x value is 0. There's no highest x value, so it goes from 0 up to positive infinity. Then range is the same thing. Y is the lowest y value is 0, and it just keeps on going up. So it goes from 0 to positive infinity. The cube root is going to be different. There's no lowest x value, there's no highest x value, so the domain is from negative infinity to infinity. The range, the lowest y value, again, there's none. There's no highest y value, so the range spans all real numbers from negative infinity to positive infinity. Yes, both functions pass both the vertical lines test and the horizontal line test. You can draw horizontal lines and vertical lines all day and only pass through one point. The vertex, this right here is 0, 0, unless of course it gets transformed, like it might get transformed to h, k, and that might be a new vertex. Here, we're actually not going to call this a vertex. We're going to call it a point of inflection, but same idea. It starts at 0, 0, and it can get transformed depending on what h and k end up being. At the moment, the x-intercept is 0, but that would change if you moved it around. And at the moment, the x and y-intercept for both of these is 0. And of course, it changes if you transform it, moving up, down, left, or right. End behavior. This function only leaves the graph once to the right here. It only leaves the window once to the right here. So you can say as x goes to infinity, as x gets larger and larger and larger, then y will also get larger and larger and larger. You can go as high as you want in the y values just by simply going as high as you need to on the x values. And so that's end behavior. You can kind of say that the cube root function has down, up, end behavior. It leaves the window here going down. It leaves the window here going up. Where is it increasing? It's increasing along the interval 0, infinity, where it's defined. And this is always increasing here. It's never decreasing. It never flattens out completely. There's no symmetry on this one, unless, of course, you're going to somehow draw the lower arm of the parabola. Then it would have reflectional symmetry. But we're just looking at this as a function. And here, there's rotational symmetry about the point of inflection right here. Let's see what happens when we start introducing some transformations. So, let's say we had the graph y equals square root of x plus 7. Well, looking at that here, we actually don't even need to look at the graph. I know there's going to be a horizontal shift of -7. I see x plus 7, and I just flip it around because it expects subtraction. So this would be a horizontal shift of -7. There's no vertical shift because there's no number on the outside of the square root. This -7 is inside for horizontal. So that means the new vertex, the old vertex would be at 0, 0. But the new vertex would be shifted over 7. It would be at -7, 0. This is the location on the graph. There's no vertical dilation, no horizontal dilation. And so the new domain would be -7, infinity. The lowest x value you could have here is 0, but because of this shift, you have a new lowest x value would be -7. The vertex shifts over -7, and so you could say the domain here is -7, infinity. The range is unaffected because it's just a horizontal shift. Moving right along, let's take something a little bit more complicated. Here you can see there's 3 different numbers. There's a 5, a +2, and a -1. The +2 is on the inside, so that's going to be horizontal. It's going to be a horizontal shift of -2. The whole thing is going to be moved over to the left 2 units. The vertical is going to be a vertical shift because I can see it's -1 on the outside. So that means the new vertex, the old vertex used to be at 0, 0, but now because of these 2 shifts, you got a new vertex at -2, 1. This is a location on the graph. Plus, on top of that, it's going to be vertically dilated. It's going to be stretched. It's going to be 5 times as steep as it normally would be. All the y values get multiplied by 5. So, what does that mean? That means that the new domain, because of the horizontal shift, you have a new lowest x value. It's -2. It used to be 0, but because of the horizontal shift, the domain is -2, infinity. And the range, you have a new lowest y value because you can subtract -1 right here. The vertex is now down to -1, so the range is from -1 to infinity. Let's go to cube root land. All right, so we've got 3 numbers here. We've got a horizontal shift, a vertical shift, and a vertical dilation. You can see x -2, so we see a -2 and switch that around to get +2, 5 is where the new point of inflection is. Used to be at 0, 0, as you can see here, but the new point of inflection, everything got shifted to 2 units to the right and 5 units up. There is a vertical dilation of 4. You can see that's the number out in front here. And there's no horizontal dilation yet. The domain is going to be unaffected. Actually, it's a lot easier than before. And the range is unaffected because, it went down as far as you wanted in both the x and y directions and went up as far as you wanted in both the x and y directions. So it's still going to be -infinity to positive infinity for both. Cube root. All right, check this out. Cube root of 7 times the cube root of x -3 over 5 plus 2. There's 4 different numbers. The -3 turns into a horizontal shift of +3. The +2 on the outside is a vertical shift. That means that the new point of inflection is at 3, 2. It used to be at 0, 0, and now it got shifted horizontally and vertically. The new it also has a vertical dilation, 7. It's going to be 7 times as steep. And the horizontal dilation is 5, because I got that from the number that's being divided right here, 5. Domain and range are unaffected. All right, let's reverse the process. Let's do equation table graph backwards. I'm gonna do the first step all together. If you are given a graph like graph A right here, you know, oh wait, is it a square root or a cube root? It looks kind of like a square root, except the vertex used to be at 0, 0, and now it's at -4, -2. I've kind of boxed it in right here. You can see that's the vertex, -4, -2. And then the next easy to read number is down here. That's -3, -3. I'll put that on the table. And then the next easy to read number is 0, -4. I can put that on the table too. And beyond that, I can't really read any easy numbers. So I'm taking a graph and I'm turning it into a table. I'm doing equation table graph backwards. They're giving me the graph. I'm going to do the table, and then next I'll find its equation. Let's just do that step a couple more times. Check this out. This looks like a cube root equation, except it's been shifted. The point of inflection used to be at 0, 0, but now it's at -1, -2. And I've boxed it in right here to indicate that's the point of inflection. And the next easy to read number is not even on the graph. It's actually over here at 6, -1. And I mean, you can't see it here. That's kind of my own error. But if you could read as far as 6, then you'd see it goes to 6, -1. It's an easy to read intersected point. Here, this also looks like a cube root, but it's been vertically dilated. It's been stretched a lot. I can see that the easy to read point is 0, 0. That's going to be the point of inflection. There's another one over here. +1, +4, boom. There's another one over here, -1, -4 right there. So we can put those on the table. I'll use them later. Again, going from an equation to, going from a graph to a table, you can see the point of inflection got shifted. It used to be at 0, 0, and now it's at 2, 1. The next easy to read point is over here, 3, 2. And the next another easy to read point would be 1, 0. I'm going to put them all on the table. The order that you put them on the table doesn't matter too much, just that you can kind of like quantify where exactly this graph is. So let's do graph A. Because the vertex is at -4, -2. That means it had to have a horizontal shift of -4 and a vertical shift of -2. Also, look, you can see the fact that it's going down, like the original, the parent function goes upwards like this, but here it's been vertically dilated by -1. I can tell that because either the graph used to go from 0, it used to go from 0, 0 to 1, 1 would be the next point, but now it's going down 1 unit instead of up 1 unit. And then it goes down 1 unit and then over 3 units, when in fact it used to go up 1 and over 3. So this whole thing has been vertically dilated by -1. It's been flipped vertically. And so then taking all this information, you can say that on the inside it's going to be x plus 4 because you switch the signs for whatever on the inside. The -1 turns into this negative out here, and the vertical shift is -2 here. Let's take a look at graph B. Well, this is a cubic function, and so the point of inflection has been shifted, -1, -2. That's where it is. So you get the horizontal shift of -1, a vertical shift of -2, and actually it doesn't. There's no vertical dilation or horizontal dilation. And here's the tricky thing: there is a horizontal dilation. If you compare it to the original, the parent function here, it would go between these 2 points, these 2 easy to read points. It would rise 1 and would run 1. It would go over 1, up 1, to go from this point 0, 0 to 1, 1. However, it doesn't do that here. It goes, in order to rise 1, you have to run 7 units, not 6, 7. 7 units to get from -1 to -6, which is incredibly stretched. It's horizontally dilated 7 times longer than it needs to, than the original, than the parent function. So because it has a horizontal dilation of 7, you can say this is x plus 1 and then divided by 7. The -1 is the +1 and the -2 is the -2 here. We can talk about that more in class if you like. C. Here, this is going to be a cubic function, and so you can see in the end result it's cubic right here. There's no horizontal shifting or vertical shifting because the point of inflection stays at 0, 0. However, there is a vertical dilation of 4. You remember, like I said just a few moments ago, going from the point of inflection to the next one here on the parent is over 1 up 1. But over here, it's over 1 up 4. So that means it's been vertically shifted by a factor of 4. It's got a vertical dilation of 4, and so then the 4 goes being multiplied on the outside of the function, 4. D, here, this is a cubic function, and you can see, because it has both arms, it's kind of like an S, the point of inflection has been shifted 2 units to the right and 1 unit up. So I have to make sure I put the 2 and the 1 into my cubic function. There's no dilations because I can see going from the point of inflection, you go to the right 1 and up 1, to the left 1 and down 1, just like the parent function does. So it hasn't been stretched at all or compressed vertically or horizontally or flipped at all. It's just been shifted. And so there it is. Thanks for sticking with me. Bring your questions to class, and I'll see you in class.